Alright friends, welcome back. In this video I'd like to go ahead and continue our discussion of Chapter 2 by taking a look at the next section of your textbook, which is Section 2.2, and in this section we're going to talk all about functions, okay? And so instead of reading through the definition, I just want to take you to this picture that I drew. No making fun of my art. I'm very sensitive about my drawings, but I do think that thinking about a function in terms of a machine is probably the most useful analogy for being able to make sense out of what a function is, right? So here's what I've drawn here, right? I've just drawn a basic machine. And this machine is built in such a way where it's going to take in inputs, right? We're going to give this machine something. And then the machine is going to do what it's programmed to do with our input. And then it's going to spit out what we call the output, okay? We do have some special notation for that, right? Particularly whenever we're dealing with functions in mathematics, we're going to be dealing with machines that we give numbers to. And so that's why we go ahead and characterize the input as x, and the output, after plugging it into the machine f, is something that we write notationally as f of x. And just so that we don't get this confused, I know that people would look at f of x and think multiplying f times x, but that's not the interpretation here. The interpretation is that I gave the input x to the machine or the function f, and it gives me the output, and that's just the name of the output, f of x, the way that that's written on the page. That's how we would read that, okay? Now, let's say, for example, that this was the machine that if I gave it a number, let's say I gave it, say, the number 3, just as an example, let's say that this is the machine that gives me that letter of the alphabet in order, right? So if I give this machine the number 3, then this machine is going to spit out C, okay? So this machine was programmed to take that number 3, to look at the alphabet, and then give me the third letter of the alphabet, and then spit that out as the output, right? So that's an example of a machine doing something with the input to give me the output, okay? Now, as another example here, let's say that I were to give this machine the number 6/2. Okay, so 6/2 I know is 3, but if I were to go ahead and plug that into the machine here, the machine is going to actually recognize that as 3 and then return C again, okay? So you may start scratching your head and being like, well, Mr. T, that is 2 different inputs that have given me the same output. Is that a function? Well, yes, it is, okay? What would not make sense would be the following situation, right? So let's say I gave this machine the number 3, okay, and again, this is my alphabet machine, and then, you know, it gave me the letter C, but then it also gave me the letter Q, let's say, okay? So when I gave it one input of 3, it gave me 2 different inputs of C and Q. Well, your face might look a little bit something like this at this point, because we know that this would not be a situation that makes sense. So in order to be a function in mathematics, if I give the machine a single input, I want to get a single output that goes with that input, right? So in this case, this would not be a function because I got 2 different outputs from one input. Again, if this is my alphabet machine, if I give it the number 3, I would want to give me C. If I give it 4, I would expect the letter D. If I give it 5, I would expect E, and so on and so forth, okay? And so one of the things that we might do is we might go ahead and give a name to the list of all of the numbers that you're allowed to give this machine. So we only have alphabet letters that count up to 26, so we know only the numbers from 1 to 26 belong in this set of numbers that I'm allowed to give this machine. So we give that a name. We call that the domain of the function. And then we get this list of all the different things that we get out of this machine as outputs. We go ahead and give that a name. We call that list the range, okay? We're going to take a look at a lot of different types of functions where the set of numbers that you're allowed to plug into the machine is going to vary from problem to problem, and we're also going to see that same thing for the range. So instead of getting too bogged down with the definition there, a little bit of an explanation as far as that's concerned, okay? Now, just so that you are prepared for a bunch of different situations, there are a ton of ways that you could represent that relationship between input and output, and I want to show you a few of them, okay? So this is something that you call a mapping, okay? And so what you're looking at here, this capital A, this represents the domain. So again, that is the complete list of all of the allowable inputs. And then this, of course, is the range, right? So these are all the outputs that we get from those inputs. And you notice what I've got here, right? I've just basically drawn a list. This is like our alphabet machine again, okay? So I've drawn a list of the numbers from 1 to 4. That's in my domain. And then I just have arrows simply drawing to what input is going to give you what output. etc., etc. Okay, so just by looking at this picture, we can automatically tell that yes, this is going to be a function, because you'll notice that there's only one arrow sprouting out from each of your inputs. Remember that it would be a problem if we gave it one input and got two different outputs. Okay, so this would indeed be a function. All right, is this a function? Okay, so this is another mapping. So we're looking at all the inputs there. And again, the only thing that you need to be on the lookout for is if you have two different arrows sprouting out of one of those inputs, that would mean that one input goes to two different outputs. I think we are good to go here. There's only one arrow sprouting out of each one of those inputs, so we are good there. And again, that might be a situation where you're scratching your head because we gave the machine the number 2, and then we gave it the number 4, and it gave us the same output of B. But remember, that's fine. Okay, we saw that situation before whenever we gave the alphabet machine the number 3, and we gave it the number 6/2. We got the same output from those two different numbers, but again, that is allowed, right? So what's not allowed is this situation right here, where you'll notice that if I have an input of 2, you'll notice that 2 goes to both A and C at the same time. That is an issue, right? That is not going to be a function in that case. So that is just one representation of what a function could be on the page, right? So that, again, is called a mapping. And there's a bunch of different other ways, too, right? So we might go ahead and describe a function verbally, right? I did that before whenever I was explaining the alphabet machine. I was like, you know, all the numbers from 1 to 26, if you plug them into the machine, you get all the different letters of the alphabet in order, right? So that would be a verbal description of what your function does. That could be a way that we represent functions, and that's for a game, right? Another representation would be numerically. Maybe I give you a table. Maybe I give you a list of ordered pairs in this way. So remember that A is your domain, B is your range, and then F equals this set in the curly brackets. You'll notice that I just gave you a couple of ordered pairs here, where, again, these follow very similar to X and Y coordinates, where the first number is the input, and the second number, of course, is the output on each one of these. Or instead of saying input, output, I and O, we could say X input, Y output, X input, Y output, etc. Okay? And this would be a function because you notice, again, all of these inputs, 1, 2, and 3, those have one and only one corresponding output. Okay, so we could do it numerically like that. We could also present you with a graph. Okay, so a graph of a function that is graphing your inputs X versus your outputs, we might say f of X. Okay, so here's your x-axis, here is your f of x axis. You might notice that in problems, instead of saying f of x, because notationally we can get a little bit bogged down by that, typically we just go ahead and say that the single variable y is the output. And so that's why you often see y is equal to f of x in this way. Okay, and one of the more confusing ones, or one of the ones that we need to kind of prepare you for, is algebraically. And you notice that I've already done some work here to save some time in the video. But if I give you an equation that relates x and y, your input and your output, the question is this, right? The question is, can y, which remember, y represents your output, can the output be expressed uniquely in terms of the input or in terms of x, right? So again, the most important word of that sentence, of course, is this one right here, uniquely. Can the output be a unique thing that we get from a single input? Remember, that's the most important part of a function, right? So algebraically, what does that look like? Well, here in a couple of examples, if I give you the equation x is equal to y plus 3, you'll just notice that I'm solving using the same general steps to get y isolated. And we end up with this. We end up with y is equal to x minus 3. And so the question is this a function? Well, if you were to say this verbally, you might say that the output is what I get whenever I take my input and then subtract a 3. Okay, yeah, that is unique. That is a unique description for how to take an input and get the corresponding output. Okay, it's not output is equal to input plus 3 and output is equal to the input minus 7, right? It's not two different descriptions to get your output for one given input. It's just one unique one. Okay, in the second example here, we have x squared minus y is equal to 8. And so again, if I just do all the algebra to solve for y, get it by itself, I end up with this. I end up with y is equal to x squared minus 8. That is a unique description. If I give you a single output, you could use this relationship and get that. Sorry, I think I said output a second ago. If I give you a unique input, then you could use this equation to get a unique output. It's right. It's not two different things. Let's take a look at an example where that falls apart. So x squared plus y squared is equal to 2. You'll notice that I just subtracted x squared from both sides and then took a plus or minus square root. And then we get y is equal to plus or minus the square root of 2 minus x squared. The problem arises whenever you start to take a look at this plus or minus right here, because again, if we interpret that, then that is one of two different things. It's either the positive square root or it's the negative square root. So that means that I have this output right here that came from two different descriptions, two different ways that I could be working with my input. And so that's not unique because of these two different descriptions. So in this case, this would not be a function right here, whereas these first two would indeed be functions. And so when it's given to you algebraically, you're going to have to do a little bit of extra thinking or a little bit of work algebraically to see if you could take that y and isolate it uniquely in terms of x. Okay, so one of the classic things to look out for is anytime you have a situation where you might need to introduce a plus or minus. Okay, and so how do you tell? Well, if y is ever being raised to an even exponent, like here it was being raised to 2, that is a red flag part right there. That means that later on in your algebra, you'd have to introduce a plus or minus square root or fourth root in the case where it says y equals 4 or whatever, okay? So anytime you have to introduce a plus or minus, you know that things are going to fall apart as far as it being a function, okay? We've already talked a little bit about function notation, about this vocabulary right here, so I just want to take a look at a couple of examples where we're just taking a look at all the different representations, okay? So here in number 1, it just says which sets of ordered pairs represent a function from A to B, okay? And so A, capital A, that represents this set of the alphabet letters A, B, and C. B represents that set of natural or whole numbers from 0 to 3. And we just have to take a look at each one of these situations and then circle the ones that maybe represent functions. Remember what we're looking out for. We're looking out for a single input that goes to more than one output. And if you take a look at part A there, I think things immediately are going to start to fall apart because you notice that, you know, an input of A is going to go with an output of 1. That's not a red flag thing there. But you notice that I've got inputs of C, and C is going to go to 2, and it's also going to go to 3, unfortunately. Okay, and so this is kind of a red flag that C is going to go to two different things, so that is not going to be a function right there. Okay, if you look at the next one down, part C, you'll notice that each one of these input values is going to go to one unique output value. Okay, it's not the case where I have repeating ones going to two different things, right? So it's not the case where I have 1 going to A and I have 1 also going to B. That would be an issue. Okay, so I think that we are all clear here. So yes, we could say that this is indeed a function. Okay, part B, again, looking for single inputs that go to more than one output. We have A, B, and C. Those go to 1, 2, and 3. I think we are good to go there. It's not the case where A goes to two different things or B goes to two different things. And then same thing for D, right? You'll notice that we have all these inputs of A, C, and B. It looks like, again, I don't have A going to two different things, B going to two different things. I don't have C going to two different things. So this is indeed a function. Okay, so again, being on the lookout for this situation right here, I have a single input going to two different outputs. That's a problem, not a function. Okay, so one of the other things that we're going to be asking you to do is to evaluate your function. And so taking it back to the machine analogy, this is where you are actually throwing something into your machine. You're giving the machine an input, and then you're going to have to do the algebra to figure out what the corresponding output would be. So that's called evaluating the function. And so here in this first example, we have a very simple machine. Here it is right here. It just says the way that you get your output, and this is how I want you to read them actually. Okay, so your output is equal to 2 times your input and then minus 3. That would be a quick verbal description of what this function does. So if you want an output, all you have to do is give me that input. I'm going to multiply it by 2 first, and then I'm going to take away 3. Okay? So you'll notice here in all these examples, what we're doing is we're saying, well, you know, what's f of 0? What do you get out of your machine if you were to plug in a 0? Okay, well, let's find out, right? Because we know what our machine does. We know that it just simply takes 2 times whatever the input was, and then takes away a 3. Okay, so knowing your order of operations here, 2 times 0 is what you would do first. 2 times 0 is just 0. 0 minus 3, that of course is going to give you a negative 3. So if I give this machine an input of 0, it's going to output a negative 3. Okay, same thing on part B here. If I were to give this machine a 4, then same function formula. I just want to go ahead and take 2 times my input, which of course is 4, and then go ahead and take away 3. Okay, well, order of operations here, 2 times 4, of course, is 8. Take away 3, I get an output of 5. So if I give this machine a 4, it's going to give me back a 5. Now, one of the more confusing bits is when you start to give it inputs that we actually don't know the value of. I don't know the value of b, so I don't really know what the value of b plus 2 is. But that doesn't mean that I can't give it to my function, because remember, we know what our function does. We know that it just simply takes 2 times whatever the input is and then takes away 3. Well, now the input is just this value that I don't know, but I could still plug it in. I still know what it is. That input is just b plus 2, and because we know algebra, we can go ahead and take care of this pretty darn easily, because distributive property says I'm going to distribute that 2 inside, so 2 times b plus 4 minus 3, and then order of operations there, I've got a couple of constants I can combine to some like terms, so 2b plus 1 would be the output that goes along with an input of b plus 2. So again, what this means is that if we knew what b was, then we would just add it to 2, plug it in. We automatically know what that output would look like. Depending on what that b was right there, I automatically would just plug that same b in right here, and I would automatically get what that output would be. So that's pretty nice. Now, part D, this represents something that actually comes up in higher level mathematics a lot, and so this just needs to be a situation that we're prepared for. What you're noticing right here, this triangle looking symbol, that's actually a Greek capital letter D. It's called a delta, but for our purposes, this is just like saying back in the day whenever we used to have something like U plus V, okay? We're just taking our input to be some kind of binomial. So the delta x right here, that is a single quantity. That's not something times something. That's just a variable name to represent one quantity, right? And so again, if we're plugging that into our machine, what is that going to look like? Well, again, we know what our machine does. We know that it takes 2 times the input, and then it takes away 3. So now our input is x plus delta x. And so, again, do this exactly the same way that we did the last problem. We're just going to distribute that 2 inside. So 2 times x plus 2 times delta x minus 3. And it would be here that we would want to combine any sort of like terms that we have. But here, because we have x and we have delta x, those actually are not like terms. We would go ahead and just simply say that that is our corresponding output. So I know that that final situation is a little bit weird. But again, you just want to look at that as taking x plus delta x to be a binomial that you're plugging in, okay? I invite you to go ahead and pause the screen here and take a look at the next one. I'm not going to go ahead and talk through it, but it's the exact same thing. You might notice that in part B, we need to go ahead and use one of our special product formulas in order to go ahead and evaluate and figure that out, but just involves some algebra. So I'm going to go ahead and move on here. Number 4 represents what we call a piecewise function, okay? And the reason that we call it a piecewise function is because you notice that what it's programmed to do is split up into a couple of pieces, okay? So this, again, is called a piecewise function. All right, and so the interpretation that we want to go with here is that this is going to be a machine that is going to take your input and throw it into one of 2 categories, okay? So whenever you plug a number into this machine, the first thing this machine is going to do is figure out if what you gave it is less than 0 or if it is something that's greater than or equal to 0, because depending on what it is, this machine is going to be programmed to do something specific depending on which category your input falls under, okay? So if you ever give this machine something that is less than 0, or in other words, if you ever give this machine something that is negative, then what this machine is programmed to do is basically do what we saw in example 2. It's going to take 2 times your input and then take away a 3. However, if your input is something that is non-negative, so in other words, if your input is either 0 or positive, then instead it's going to do this with your input. It's actually just going to square that number and give that back to you as your output, okay? So again, we call these piecewise functions because we kind of split it up into 2 pieces in this way. So the first thing this machine does is categorize what you give it and then do something accordingly with to get the output, right? So here in the part A here, it says h of negative 2. Our input here, of course, is going to be the number negative 2. The first thing our machine is going to do is categorize that input. That, of course, is a negative 2, so that's a negative number. So that means it's going to follow that first piece of the piecewise function and do this with your input. It's going to take 2 times your input and then take away 3. Okay, so our input here is negative 2, so 2 times negative 2, of course, is negative 4. Take away 3, we are simply going to get here a negative 7 for our output. Okay, so that's not too bad. In the next example here, we're going to give our machine a positive 4 that is non-negative, so the only thing that the machine is going to do with our number here is simply square, and we are going to get a value of 16 whenever we do that. So if we have an input of positive 4, we get an output of 16. Here in this last example, we have yet another one of these cases where what we are plugging in is something that we don't really know the value of. And so that's going to kind of present a challenge for us in a piecewise function, because if we don't know the value of our input, we may not know what category it falls under. But if you look closely at our input here, you'll notice what it does. It takes our unknown number here, a, and it squares it first. After it does that, it's going to add 1. if you think about all the different ways you could plug in an a, there's really no way that you could plug in something for a and then square it and add 1 to get something negative. So this is something that is always going to be non-negative, and so we automatically know that it's going to follow that second piece of the piecewise function. Okay, so we automatically know that it's just going to go ahead and take whatever we give it here and square it. Okay, now what does that look like? Well, this is where we're busting out our algebra skills, because what we basically have here is something that looks a lot like u plus v all squared. Okay, so that's one of our special product formulas. We know that that is going to break up into u squared plus 2uv plus v squared. So I'm just going to go ahead and apply that formula here really quickly. Playing the role of u is a squared, so that would be a squared squared, or in other words, a to the fourth. And then plus 2 times u times v, that would be 2 times a squared times 1, or in other words, 2a squared. And then follow that up with a plus 1 squared for v squared, and that's just simply 1. Okay, and so again, using your algebra skills to figure out your corresponding outputs depending on what your input is, very, very important. Just be on the lookout for piecewise functions that categorize your input first and then do something accordingly. Number 5 I've already done for us here. This involves your absolute value function. Remember that it is the distance away from 0, and so you'll notice that in parts A and B, those are ones that I can evaluate very simply. Part C, because what I'm plugging in is something I don't know the value of. I don't know if that is always going to be positive. Matter of fact, it's not always going to be positive. It might be negative sometimes. The best I can do is just plug it in and then just write out the function formula in that way. Part 6 here, what we are doing is we are figuring out what you call a difference quotient, which is a very, very important quantity whenever you reach higher level mathematics, okay? And so you notice that we were given our function machine up here. This does something very simple. It just simply takes your input and then subtracts a 2. That's how it gets your output. And so you notice that the difference quotient is defined in this way. It's f of the quantity 2 plus h minus f of 2, and then all divided by h. Well, you notice that I've used 2 different colors here because, again, what they're asking us to do is to find the difference of 2 different outputs in the top and then to divide the result by h simply. So f of 2 plus h, I just did that in green. You'll notice that I did all the steps for that. I'm just plugging in 2 plus h into my function formula up here. And then if you do the algebra on that, the 2's are actually going to cancel for you, just simply leaving you with h. And then in blue, where I'm doing f of 2, again, I'm plugging in my 2. You'll notice that your 2's cancel, just leaving you with 0. And so that's why f of 2 plus h minus f of 2 just happens to be h minus 0, which I've kept the coloring the same. And you notice that h minus 0 is simply just h. If you do h over h, then that is going to give you a simple result of 1. And you notice that I just tacked on a simple note there that says all this stuff that I just did is something that is perfectly allowed as long as h is not allowed to be equal to 0 because I'm dividing by it, okay? Next up here in the video, we want to talk about domains of a function. This goes really quickly. Again, we're just looking out for the same things that we've been looking out for in the past. Any sort of denominators, we have to say that they're not equal to 0. Anything under a even square root or a 4th root, 6th root, whatever, we're going to have to say that that is non-negative, okay? Turns out to not be an issue in this first example here, 2x squared plus 1. We can plug in anything we want for x and not violate any of our rules here. So the domain, which I'll represent by a cursive capital letter D, that is just going to be the all real numbers. So the open interval from negative infinity all the way to positive infinity, representing that in interval notation just like we always have, okay? In the next one here, we notice that the denominator is x squared plus 10x. That is something that we have to say is not allowed to be equal to 0 because that would violate one of our rules of algebra here. So I'm going to say it is not equal to 0, and then I'm going to just simply solve that inequality there. Well, on the left-hand side, I've got a polynomial. I could just simply factor out an x and say that that's x times x plus 10, and then zero product property says that x is not allowed to be equal to 0, x plus 10 is not allowed to be equal to 0, and if you solve that second one, x is not allowed to be equal to negative 10. Okay, so if you were to write that domain out, we would have to go ahead and use a little bit of a union symbol and say that would be the open interval from negative infinity all the way until negative 10. Unite that with the open interval from 0 all the way to positive infinity. Okay, so we've talked about domains of expressions before. You might need to go back and watch one of those chapter P videos for more background on this, but again, we're just kind of dipping it into the context of functions here, okay? And now for this last example here, number 9, again, we have a part under the square root. We have to say that that part under the square root is non-negative because we can't take the square root of a negative number or else we are going to be joining the complex number world, right? So x plus 6 has to be greater than or equal to 0, in which case x is going to be greater than or equal to negative 6, okay? However, we also have a denominator here in this problem, so if I go ahead and say that that is something that is not equal to 0, then we'll see here that another restriction on x is that x is not allowed to equal negative 6, okay? So if you were to actually go ahead and combine these two descriptions here, x has to be greater than or equal to negative 6, but then at the same time, x cannot be equal to negative 6. If we combine these, then that would result in the simple expression x is strictly greater than negative 6, okay? And so writing that in our interval notation, we would go ahead and simply say here that that would be the open interval from negative 6 all the way to positive infinity, okay? And then a couple of final questions here. It just says in numbers 10 and 11, find all real values of x such that f of x is equal to 0. All you would simply need to do here is just go ahead and set these functions equal to 0 and then simply solve. So I'll go ahead and set those up here really quickly for us. So you notice I'm just erasing f of x here because I'm just going to set these equal to 0 and then solve accordingly. I'm not going to go ahead and show the work for that because these would just be simple quadratics to solve, but you would just go through and solve these equations, get your x values, and then that would be it, okay? In these last couple of examples here, it says find the value or values of x for which you get these outputs to be equal to each other. So the output of x is equal to the output of g. I'll just do one of these examples here, right? So if we want f of x to be equal to f of g, then I'm just going to substitute in their function formulas. So f of x is x to the 4th minus 2x squared. G of x is going to be simply your 2x squared. And if we were to solve this like a polynomial, I might go through and subtract 2x squared from both sides. In which case, on the left-hand side, I would have x to the 4th minus 4x squared is equal to 0, and then solve the polynomial equation from there. The next step would be, of course, to simply factor. And so if I factor out an x squared, I'm going to be left with x squared minus 4 is equal to 0. And x squared minus 4 is a difference of two squares, so x squared times x plus 2, x minus 2. And if you go ahead and follow up the ZPP, you'll notice here that x is going to be equal to 0 and then positive or negative 2 as your results there. So if you were to plug in any of these inputs, 0 or positive 2 or negative 2, into these two functions, you would get outputs that are exactly equal to each other, okay? It would be the exact same thing for number 13. You would just want to set them equal and solve. So I'm going to go ahead and skip out on that one. But I hope this video has been of some help to you. Sorry for the longer one here, but again, just taking a look at all the different things we could be doing with functions. Again, this should all be a review of previous algebra courses. So if you guys have any questions, then feel free to let me know as always, but keep that machine analogy in mind. I think it's really helpful. Thank you very much, and I'll speak to you guys in the next one.